Good morning, everyone. My name is Pushpa Jyothi Dudala, and today I will be presenting my project on Zephyr RTOS, a modern open source real time operating system that quietly becoming the dominant platform for connected embedded devices. Now, let's dive into the project. Before diving into Zephyr, let me quickly set the foundation. An RTOS. What is an RTOS? A RTOS is a real-time operating system. It's not like Windows or Linux. The goal is not to give you the best user experience or run a lot of apps. The one job of RTOS is to guarantee the task finishes within the strict deadline. This property is called determinism. As you can see in the table, a general OS like Windows try to maximize throughput but gives you no timing guarantee. And RTOS like Zephyr promises a deterministic guaranteed response. It also has no virtual memory. Instead, it uses fixed static memory. So every allocation is predictable. Missing a deadline in embedded system does not just mean a slow up. It can mean a airbag doesn't deploy or medical device fail. That's what determinism matters. Now let's go to another slide. What is Zephyr OS? So exactly what is Zephyr RTOS? It is a free open source RTOS hosted by Linux Foundation under Apache 2.0 license. What makes it so special? What makes it special is that it can run extremely constrained hardware. We are talking as little as 8 KB of flash and 5 KB of RAM. That's tiny, right? At the same time, Zephyr is a complete software platform. It's not just a scheduler. It ships with networking stacks, Bluetooth, file system, and security libraries and device drivers in all in one package. It supports over 600 boards across ARM and other architecture. You will find Zephyr inside smartwatches, industrial sensors, medical devices, and edge AI platforms. Okay, why Zephyr OS? So why choose Zephyr OS over dozens of other RTOS out there? First is a vendor neutral. The Apache 2.0 license means no royalties, no lock-in. Second, it has unified hardware abstraction. You write your code once and can swap the target code without rewriting a single line of driver code. Third, it comes with enterprise-grade built-ins out of the box. Means TSL 1.3, Bluetooth 5.0, PSA security with the other with free RTOSs, other RTOSs, you have to add all these separately from different vendor SDKs. And critically, no single company controls Zephyr. It is governed by the Linux Foundation, which means the community drives the not roadmap, not Amazon, not Microsoft, not any chip maker. Let me make this concurrent with direct discussion to free RTOS, which is the most popular RTOS historically. Free RTOS is a great scheduling kernel, but it was designed as just a kernel. For devices and networking, you are tied to whatever SDK your silicon vendor provides. Suppose if you start a project on STM32 and need to move to Nordic, you essentially rewrite everything. With Zephyr, the device tree and concrete system, which we will study in the later slides, create a unified abstraction. Your application code, network stack, and drivers call stays the same. You just change the board target. And governance wise, FreeRTOS is owned by Amazon. Zephyr is a Linux Foundation neutral. For security, Zephyr has PSA certifications, MPU isolation built-ins. FreeRTOS security depends entirely on your chip vendor's SDK. Now, let's look into historical background. Let's look at where Zephyr came from. It actually started in Belgium. A company called Ionic Solutions built a RTOS called Virtuoso for DSPs. When River acquired them in 2001, rebranded it as Rocket and open sourced it in 2015. In February 2016, Wind River donated it to the Linux Foundation, which renamed it as Zephyr and released version 1.0. Since then, it's grown rapidly. 2019 bought Device 3 and CMake. 2021 saw the first long-term support release. 2024 added Rust support, added Rust language support and multi-core SMPs. And by 2025, Zephyr 4.1 is recognized by its contributors as the best open source RTOS in existence. It's gone from donated kernels to the most active embedded OS project in less than 10 years. Okay, what are and now look at what are the goals and purposes of Zephyr RTOS. Zephyr RTOS was designed with six clear goals in mind. First one is small footprint. The kernel fits in under 8 KB flash. Scalability. The exact same code runs on a tiny sensor node or a complex industrial gateway with full networking. Third one is safety and security. Memory protection, stack overflow detection, and thread isolations are core, not add-ons. Fourth one is hardware portability, 600 plus boards, no vendor lock-in. Fifth one is open governance, Apache 2.0, no copy left under Linux Foundation control. And last one is developer productivity, one unified toolchain using West CMake config and device tree for every board. Now let's look into the Zephyr architecture layers. Here is the visual of how Zephyr is structured internally. At the bottom, you have the actual hardware, ARM, RISC-V, and others. And above that, there is a device driver which gives every peripheral a standard API. ZPIO looks the same on Node as it does on STM32. On above that, there is a kernel which handles scheduling threads, timers, and memory. Then OS services, networking, Bluetooth, file system security, all options, and kconfig selectable. And at the top, your application code interacts with all of this clean, consistent Zephyr APIs like kthread creates and ksemptic. Each layer exposes what the layer above needs: clean, modular, and separation. Now, let's look into the development environment setup. Zephyr development toolchain has three key pieces you need to understand. Kconfig is the feature configuration system borrowed from the Linux kernel. You write .trj.config file listing only the features your project needs. Kconfig then generates a header file and only those features get compiled. This is how Zephyr stays tiny despite having hundreds of subsystems. Device tree is the hardware description. Instead of hard coding peripheral addresses or pin numbers in your C code, you describe the hardware in .dts file. This means the same application can run on different boards just by changing device tree overlay. Open OCD is the on-chip debugger. It bridges your PC to the microcontroller over ZTAG or SWD, letting you flash firmware and run ZDB debugging on real hardware. In Zephyr, the West tool calls it automatically, which is the coolest thing, right? Now let's go to another slide. Now let's go inside the kernel components. There are six components. The scheduler is a primitive and priority based. The highest priority thread, the highest priority ready thread always gets the CPU. If a high priority thread wakes up, it immediately permits whatever is running. These are independent unit execution. Each has its own stack and a priority. Timers or software timers driven by the hardware clock user for periodic tasks like sensor reads or communication timers. Semaphores, both binary and counting, let thread signals each other and control access to shared resources. And mutex provides mutual execution with priority interface, which solves the classic priority invention problem. Events use 32-bit flag register where each bit represents a condition. A thread can wait for any one bit or all of them to be set. Now, beyond the kernel, we have subcomponents and their functions. Beyond the kernel, Zephyr ships a full set of subsystems. The device driver model gives you every peripheral like GPIO, SPI, IC2, you can UCB, a unified API that works identically across all supported boards. So the networking subsystem has a full dual stack, means it supports IP4, IP6 implementation with the BSD sockets and plus the TCP, UDP, TSL means TSL and HTTP built-ins. Bluetooth is a complete stack host and controller compliant with Bluetooth 5.0, including mesh and LE audio file system. FATFS for SD cards, little FS for Node Flash, and security. Medbed TSL cryptography plus trusted firmware on trust zone hardware for hardware isolated, secure and slaves, and power management handles it'll suspend and deep sleep, coordinating across all device drivers before CPU shutdowns. This is these are the subcomponents and their functions in Zephyr RTOS. Now let's look into another slide. Now the complexity and cost of implementation. Let's look into it. Let's look into this one. Nothing is free. And Zephyr has real costs, mostly in time, not money. The learning curve is genuine. A developer new to Zephyr needs to 2 to 6 weeks of focused onboarding because they have to learn C, make K, config, device tree. These are the development setup tools, and we need to learn it all at once. If the target board is not ready in mainline repo, writing a broad support package takes 1 to 3 weeks of engineering work. Finally, though Zephyr is completely free, Apache 2.0 means no per unit royalties, no license fees, no vendor contacts. The entire tool chain, GNU ARM is also free. If you need commercial support, companies like Linaro, Foundries.io offers paid contracts, but the core platform itself costs nothing. And let me give you the honest picture about pros and cons of Zephyr RTOS. On the advantage side, it's completely free and vendor neutral. 600 plus broad supported out of the box, full networking and security inbuilt, 2000 plus active developer, PSA certified, and you can stimulate your app on a regular PC before you even have the hardware. On at limitation side, the learning curve is steeper than RTOS. Context switch latency is higher than some specialized RTOS. Though the team is actively working on it, there is no dynamic module loading. So firmware updates requires replacing the whole image. And safety certification for auto me-too or medical use still requires significant external work, and debugging complex configurations can be time consuming. Zephyr is not the right tool for every job, but for complex IoT products, it's hard to beat. Now let's look into the other slide. So what companies is using Zephyr RTOS? Zephyr has a strong industry adoption. We know that. So Nordic Semiconductors is probably the most prominent. Their entire NFC's Connect SD, which is officially platform for NRF 52 and NRF 51 devices, is built on Zephyr. And Nordic engineers are among the top contributors to Bluetooth and ST, LTM, LTEM subsystems. Intel was founding a supporter and uses Zephyr for sound open firmware in audio DSP chips. NXP Semiconductor supports their LPC families through Zephyr. STM Electronics contributes broad definitions and drivers for the full STM lineup. Google and Meta have invested engineering resources in connectivity and AI subsystems. Linaro, Infineon, and Texas Instruments round out the ecosystems. This level of industry support is why Zephyr quality keeps improving. It's not a hobby project. Now look into the future trends. Where Zephyr is headed. Edge AI is the biggest trend. TensorFlow Lite for microcontrollers is already integrated, and support for NPU drivers is coming as a chip vendors and ML accelerators to their microcontrollers. Rust support was introduced in Zephyr 1.1. The community is actively expanding Rust bindings for kernels, which will reduce memory safety bugs significantly. Safety certification IEC 61508 or becoming mandatory as automotive and medical products adopt Zephyr. Multi-core computing is growing. Modern IoT socks run Linux on application cores and Zephyr on dedicated real-time code. Zephyr is improving in SMP and AMP support for this. On OTA updates for standardized MCU boot plus manifest will give Zephyr a full standardized secure over the plane updates mechanism. It's not cool, right? Now let's to wrap up. Zephyr RTOS has gone from donated wind rival kernel in 2016 to the most actively developed open source RTOS in under 10 years. Its success is not one breakthrough, it's consistently good and good architect. It's from consistently good architectural designs, a monolithic kernel with a static allocation, device tree based hardware abstraction, compile time module, and Apache 2.0 governance model that keeps it vendor neutral with backing from Nordic, Intel, NXP, and with the ST companies and with Edge AI, Rust, and safety certification on the roadmap. Zephyr is well positioned to be standard RTOS for the next generation of connected embedded products. And thank you for giving this opportunity. Bye.